Hi, I'm back. It has been a while, and now we are at the last lecture. Yeah, lecture 16. So let's just go ahead and see what have we been at. So now the last topic is still in the same method, the same concept with the last two lectures. Last two lectures we talk about the thing that we call the hypothesis testing. Oh, by the way, the mic, the clip, and the writing may not be in sync. I think the mic and my camera is like 1 second delay, so please don't mind that. So we talk about that, right? And we have two classes. The first one is when we deal with just one single sample. And that was the easy case that we can just use the bell curve and just compute the score p value, and then decide whether we want to keep the hypothesis or we want to reject it. In the 15th lecture last week, so we talk about two samples instead, right? And again, this is more common because usually you have like when you want to conduct a scientific experiment, you want to test if something is true, and then you have to have two different groups to say that whether what you believe has any positive effect on on your patents, on the products, on stuff you are experimenting on. And so this will still the same concept, the same test, just tiny teeny bit of changes. If you understand the first one, then you should be able to follow the next one easily. So now we are at the final topics, which is again still the same concept. We still do the hypothesis testing. Oh yeah, I think that the name of the topics are kind of confusing, because this one is actually, again, this is also a part of hypothesis testing. You have some hypothesis, you believe in something, and you want to conduct an experiment. In this case, statistical experiment, that you have to collect samples and see if what you believe at first holds true. Right. The first one we have one sample, the second one we have two samples, and now the last one. This is kind of like, let's just say miscellaneous. I don't know how to pronounce that word. Anyway, it's like something else, but it still has the same idea, the same concept, that you have to go from hypothesis to sample collection to computing something to state your final decision on whatever you are working on. But now we have different sets of requirements. We have different types of problems that we can work on, and so that requires different methods. So let's just take a look at these nice what is it called, flowchart, right? So we have to start from the hypothesis, and instead what significance level you want to set it at. And then you have to go right through. You collect samples. You represent that set of samples as a nice graph. You get some numbers like the means, the variance, and the proportion. You use some math, and then you use whatever method, and then that brings you to the final decision that you make. So now this thing is still that thing. We are still dealing with that part, but just different sets of problems. So let's just go ahead and look at what we are at now. So what we have talked about. Oh, by the way, we have talked about parameters, listing. And I think I have to move, yeah. We have these 3 different main parameters that we can immediately get from the samples. You can get a mean, that's easy, just sum everything up and divide it by n. We cannot get a proportion, again, just count how many of the things we want to look at and divide it by the size of the whole samples. We have the variance. It is a little bit more complicated, but again, it's just like you get from your data, you get a single number s. And the problem we have is that we cannot get the exact number for the population parameter for whatever reasons. So we have to kind of like take bargains and get something that's close enough, which are these 3. And we explain how to get. Oh, actually, we already touched these 2, not this one. Okay. So now we are talking. We are going to learn how to get that thing, that variance, right? And also other things, whatever it is. Maybe the question, your hypothesis might be something like different. We will see. So let's take a look at what kind of problems you can work on. Oh yeah, by the way, before we can make some assumption and perform hypothesis testing on the means and proportions, we are required to get strict assumptions. Right. That means we need to have a large enough sample size. We have to know the variance beforehand. Maybe we have to, I don't know, get some. Oh yeah, we have to get a number. Like that has to be continuous. We cannot deal with the discrete probability function. Okay. But what if we don't? What if we cannot get all these like requirements? Then everything breaks. So you have to find something else, a different method that you can use. We always use not actually always, but we actually deal with just these 2 things, like the mu and the p hat, or just a p, just a p. Can I? Oh, I can't. No, I forgot that I can't just like Control 3. My keyboard is not connected to my laptop anymore. Right. So if we want to get some values, some numbers from something else like variance or whatever numbers here, then we have to use again a different method, and we can use less information from the data. Okay. And that's kind of like the same thing with that. We don't need to know like all these like 5 numbers. When you perform the hypothesis testing, you have to have mean, you have to have variance, you have to have like large enough samples, and other stuff. If we don't, then we have to find a different way to do this. And of course, since we don't have like all these numbers, then the test is going to be less powerful, as in like the final result would be less convincing, would be less accurate, I would say. So now that we know this thing, we just skip just to some definitions. Yeah, not a good one, but let's go. Let's get it real quick. So this method, like this has like a big name called a non-parametric method that works with the enumerative data. What it means to be enumerative? It means it just like you count how many things, how many objects are in a certain category. So you have different categories. You don't have a continuous data like height, weight, temperature, income, or whatever. You have like boxes that are separate. You will see in a moment. This one does not deal with specific population parameters, so not these 2, and everything else. Right? This method doesn't require assumptions about whatever distribution it is. because to perform the hypothesis for mu and for p, I'm missing a p. For mu and p, we have to always assume that they are in the bell shape. If they have like different kind of like distribution, then again everything breaks. So it has to be the bell shape to do what we have done 2 weeks ago. If not, then we have to stick with this new thing. So let's go ahead and look at what new thing it is. So it has a name. This test is one of the non-parametric methods, whatever it is, right? And this is more common. This is kind of like this is actually the more like general way of thinking when you have to deal with data. Like you don't like if you haven't learned statistics at all, then you have no idea about the bell curve. You have no idea about the distribution function. You have no idea about the random variables or those sort. But for this one, you don't have to know all those things. You have to know like some of the main concepts, but like you don't have to go down all the paths. So in this case, we have chi-square test. So let's take a look at one of again my favorite card games, Hearthstone. So in Hearthstone, there are 4 different types of rarities. So we have common, or as in just like bad cards or common cards that people put in decks. Some of them are good though, like they are in every deck, but most of them are just like bad. We have rare just like slightly better. We have epic, again kind of better but like niche. You use this to perform some crazy combo, but not in competitive settings, I would say. And we have like one of the best. Have like the best cards, like the cards that like define your deck. If you want to play this deck, you have to pack these legendaries, or maybe 2 or 3, and then you fill in the rest of the deck with all other cards. So they kind of like promise that if you open a pack, this is the distribution you will see. So you have a 71.5% to get a common, you have 23% to get a rare, 4.5% to get an epic, and you 1%, just 1%, to get a legendary. So this is what they want you to believe. Maybe it's true, maybe it's not. But let's say this is the number that you are told. And then of course, let's say you have money, you go ahead and open lots of packs, 200 packs to be exact, and you get 1,000 cards. And that's all the cards that you get from those packs. You get 718 common cards, you get 227 rare cards, you get 47 epic cards, and you get 8 legendary cards. So you are looking at this and say, this number doesn't quite match the number that they gave you, right? And if you do the math, then if you actually get if there is like actually 1% chance to get a legendary, then out of 1,000 cards, you should get 10 legendaries, right? But now you get 8, and you say, is it? Am I just unlucky, or are they lying to us? Like you can't say, you can't tell. And here we are trying to see if they were honest, if the distribution are actually what they have promised, right? From that 71.5 and so on to this, the samples that we get, right? So the question is you want to compare the samples to the distribution and be able to decide whether it is common or not. Okay. So in this case, let's go ahead and see if we can use the same method from back then. Like we can use a bell curve, we can compute the p-value, other stuff, other, And of course we can't. There are problems everywhere. Like what are the problems? So first problem is we can't. Maybe let me start from that, right? The first problem is that the category is not numeric. I think it should be numerical, but anyway. Why? Because we now have 4 different buckets. We have a bucket with common cards, we have a bucket with rare cards, we have another bucket with epic cards, and we have a bucket with legendary cards. So, how can you get a single number out of these 4 buckets? Right? So you cannot get like something. You cannot put them all into a single line and linear scale. Like to say that and common is worth 1 point, a rare is worth 2 points, and epic is worth 10 points, and legendary is worth 800 points. Right? You cannot do that. There's like nothing in between. So you cannot perform the hypothesis testing about the meal. And we don't have the variance, because that's all they have promised. We don't have the variance. So if we don't get the variance, then again everything breaks. Because all the formulas you have seen involves as a variance somewhere. And you may ask, okay, if we are, it seems like we are talking about proportion, right? It's percentage, and percentage is like proportion. So can't we do just the proportion? The answer is yes and no. Yes, as in right, you can do it, but the problem is you can do it 1 by 1. What I'm saying is, if you want to test a hypothesis about the percentage, the proportion of common cards, yes, you can do that. But then you don't get any information about the rest. You don't get any information about the rare cards, epic cards, and legendary cards. If you start with your hypothesis about the common cards, then you cannot use the result to conclude anything about the other rarity or other cards, right? So you can pick one, but at the end you can only conclude one. You don't get the whole picture. You don't get to make a decision or say something about the whole box itself. Right? It's just gonna be like just that one, or just that one. But what we are trying to say is we are trying to see if they actually have this kind of this kind of distribution, where this is the amount of common cards, this amount of rare cards, this is the amount of epic cards, this is the amount of legendary cards. Right? We want to get the whole picture. We want to say whether the distribution we got at the beginning from the Hearthstone developers is true or not. Okay. And to answer that question, we cannot just test one and research and get a different samples. Test another research and get a different samples. Test another research and get a different sample. Right. That will take too long and also too much money. If you don't have that much money to spend on. So we may believe that this follow another distribution. So to perform the hypothesis testing for 2 previous weeks, we assume that this is a bell curve. It's a nice curve right there. What if it is different? If we believe it's something skewed to the left, to the right, or maybe something flat, or maybe something whatever, crazy shape. So we cannot start with the assumption that it is a nice bell curve. So these are all the problems that why we can't just do the same thing. So now we are trying to introduce the new thing. But before we get to the numbers, the formulas that again you will get in 10 minutes. So let's get back and let's see if what we can do about this problem. Right? All we have are just 2 sets of numbers, 2 sets of enumerative data frequencies. Right? We don't have variance, we don't have the bell curve, we don't have anything. So if we have just those 2, what can we say? So our now hypothesis might be, I'm saying it might be because we can state it in different ways, but like the intuitive way to state that is we want to believe, because that's what they say. We want to believe that the distribution is exactly what they have stated. Let's say that there's 71.5% chance to get a common card, 23% chance to get a rare card, and so on. And so we can like combine all those things and put them into one single now hypothesis. That's what we have here, right? And that's fine. Like that's a hypothesis. We can test it somehow. But then the question is, how should we test it? And but before we go there, so when should we reject these hypotheses? So just answer that in a single question. When should we reject these hypotheses? The common sense is, of course, we should say that we reject this thing if it differs too much from what we believe. If we get a sample, let's say the sample that we have above, when we open 200 packs to get 1000 cards, if that distribution, the proportions differ too much from what we believe, we should reject. So this single line here or there, I don't know where, there, right? This single line is like the whole concept, the whole, the main concept of what we are trying to. We are trying to get a single number, and we say that if that number is like if that differs too much from the thing it should have been, then we say okay, that's the rare occurrence. Or we say that our assumption was false. Yeah. So that's just the idea. If the number differs too much, we will reject it. The next question is, what is too much? Right. If I'm saying that if the number is 71.5 and I get 71.6, does it differ too much? Or do you think it's still acceptable? What is your tolerance? What is my tolerance? If it says 23, is 22 too far? 21? 20? Right? So we agree that it fails. We will reject if the numbers, if the proportions differ too much. But then we have to again define what it means to be too much. Yeah. And we can, of course, we can just take the difference. If they claim it's 21.5 and we get 21.3, then the difference is, just like subtract them from each other, which we get oh yeah, I can write. I forgot. Sorry. So what we have here is this is what they have told us. And this is let's say promise. They promise that, and then what we get from sorry about the logo. Let me move that a little bit. Yeah, that works now. What we get here is we get 1.8 because that's 700 out of 1,000. 227478. We have to move. Okay, there. 227478. Right. So this is all we have, and we are trying to compare. We are trying to compare them and see if they differ too much. Right, and we can measure the difference again by just taking the absolute difference. Right, that's one way. Just take the difference. 71.5 and 108.8. The difference is 0.3. So now I'm talking about the difference, not without the design. So you take the absolute value. The difference between these two values is 0.3. the difference between the next two values is again, I think, yeah, 0.3. This is 0.2 and this is 0.2. I kind of like have to move around. Alright, so now we get some nice kind of nice numbers. So the next step is, can we use this number, this difference, to work out to get some values? Okay, so we what we did right there, I think, yeah, there. We simply like take the difference and sum them up and see if the difference is high or low, right? Intuitively, if the difference is 0. So for example, if we actually get 71.5, 23, 4.51, then the difference in this case would be like 0, 0, 0. Right? If the sum of the differences is 0, then that means these two values are these two sets of values match exactly. So we will be happy to not reject if the value, the result is 0. Right, so if it's 0, then we are happy, right? That means if it's too high, we will be not so happy. If they differ too much, if this sum of differences is too high, then we say, okay, that means they differ too much. Oh, and in this case, when we say that the difference is too high, since the formula we have, I have to like, if the formula we have here, or since the formula we have here is a sum, right? Then we don't care if that difference comes from 4 different categories or just one category. So for example, if we happen to have, let's say, 71.5, 23, let's say 10.5. Oh no, that's not how it works. So the top one for the commons is still the same. Let's say that this is 10. This is 14.5 is 1. The difference from this, let's say that's sample 3, that's sample 2. Like from that, the difference from this this third sample to the original distribution would be like 0. This is 10, 10, and 0. Right. But in this case, these two categories differ too much, and that will give us the sum of like 20. Which intuitively 20 is like, that looks too high, like that differs way too much. But then again, even if like we have things, if these 4 values are kind of close, but they are like not close enough. For example, if let's say we have let's say that number is 2, 3.5, 22, and 72.5. Let's say again, that's the first example. Let's say we have enough money to do this every day, all day. In this case, the difference is 1, 1, 1, and 1. So it seems like we have small differences in each cases, but the total of differences adds up to something that is kind of high. Okay. So in this case, even if like each of them is a little difference, then the sum is kind of high. So again, in this case, we might want to say that it differs too much. And if it differs too much, then you might believe that they are lying to us. The correct distribution might be something like that. So, we may again. Yeah. So now we are taking into account of all the differences between what they have promised and what we got from the temple. So this test statistic kind of reflects what we are trying to measure. Like they add up all the differences and see if that sum of differences is too high or not. Right. So now we can look at the definition now. But notice that I'm writing kind of a simple version. But what we actually use have to still take into account of the ratio. So this one, the formula has two differences. First, instead of using the absolute value, what we have up there is the absolute value. But now we are using the square, which kind of measure the same thing. Right? If they differ a lot, then the result should be high. They just have like different magnitudes. and when we put a square here, it kind of like changes the whole curve. But the actual reason why we put a square here is that square is a lot easier to compute than the absolute values. Not compute, but easier to deal with. Because when you have a square, you can expand, you can combine stuff. But when you have the absolute values, you have to always divide it into different cases. If this is positive or negative, and so that's too much work. So we almost always stick with the square. And we also have to take into account the actual number itself. Because what we have up there here, so we want to get a number that says whether the expected number and the sample differs too much. If you expect 71 and the result is 70, right? The difference is just 1. And you can see that if you look at like a ruler or something, we have this is 70, this is 71, right? It moves just a little. So in this case, the difference of 1 is small. But on the other hand, if you believe it is 2 and the result is 3, now that's big. That's big. The difference is still 1. It's from 2 to 3. You add 1 to that value, right? But on a scale, if 2 is here, 3 is there. And you see my fingers move a lot more than the first case. If I just break, right, this is the difference of 1. And when you compare 2 to 3, that's the green part is the difference. But when you compare 70 to 71, right? 70 is something like that, but 71 is just that. You add just 1. Once we scale these two values to be to have the same scale, then the value of 1 looks so much different in those two. In this case, this is 1. This is also 1. Right? But it the influence of that one, of that little noise. Okay, let me look at they both have a difference of 1, but the influence of that addition of that noise to the whole quantity is different. The first case you add 1, that doesn't matter. In the second case you add 1, it's like you add that you add that by 50%. So that's the reason why we have to scale that by divided with the size of the original expectation. So now we have kind of digest this formula into different parts. Oh, and that again we have to sum up all the difference. If we have 4 buckets, we have 4 categories, then we just sum up these 4 values, and those 4 values we give us what we call the chi-square statistic. So that's a chi-square, and that will give us a single value. Let's say, I don't know, 5.3. Now we have some number to work on. We have a number that we can make adjustment. We can compare that. We can do various stuff with it. Right. So we use that number. We use the chi-square statistics, the result, to make a decision. So before we go, okay, so let's cut it here, and I will give you an example next clip.